Welcome, ladies and gentlemen. Back again to our Algebra 2 class. Tonight we're going to take a look at Section 5.4, Complex Numbers. Some new vocabulary. We're looking at imaginary unit, pure imaginary number, complex number, and complex conjugate. So before we dive into the imaginary numbers and complex numbers, let's take a look at some rules of exponents. Quick refresher here. Our product and quotient properties of square roots. If you have the square root of a times b, that's equivalent to the square root of a times square root of b. Same thing can be done with division. So the square root of a divided by b, square root of a divided by square root of b, provided b does not equal 0. So as far as simplifying goes, when I look at things like square root of 50, if it's not a perfect square, I want to try to use my idea of a factor tree to say, okay, what can I make 50 using perfect squares? So for instance, that would be something of the form 25 times 2. Now there are other ways to make 50, but those other ways like 5 and 10 don't include perfect squares. I'm trying to make perfect squares here. Now the reason why I can make a perfect square is this can now be split up into the square root of 25 times the square root of 2. And the square root of 25 is simply 5, so this becomes 5 root 2. So there's a quick refresher on how to simplify radicals. Alright, so let's dive in. Now, why is the radical so important? Well, the radical is so important because we have things with square roots of negative 1s. And we've said before, you can't do square root of a negative. You can't do square root of a negative. You can't do square root of a negative. Well, now suddenly, we can. And that's what we're going to talk about here today. So, I, the imaginary number, yes, I is a number, not in fact just a letter. So the imaginary number I is defined as I squared equals negative 1. This I is the principal of the square root of negative 1. That means I actually is square root of negative 1. And hence I does have a number. Now a couple things when you write I don't want to see this. Because what happens is you start to do this, and then you start to dot the dot the I on the top, and it begins to look like a 1. When you draw your I, put the little hook on the bottom, put the dot on the top. That's I. Not a letter I, that's the number I equal to square root of negative 1. This I is what we call the imaginary unit, and when we put a real number in front of that, we get a new number which is called a pure imaginary number. Those are things like 3i, negative 5i, I squared to 2. Those are all pure imaginary numbers. Alright, so let's try to simplify. Square root of negative 28. What I can now do is, much like I did with the square root of 50, is I can take negative 28 and I can try to split this up into perfect squares. And when it's a negative, the first thing I want to multiply in is the negative 1. Get that negative by itself. So we'll go negative 1, and I'm thinking, okay, what multiplies to give me 28? I got 2 and 14, but again, we're looking for perfect squares. So the only ones I can really think of here are 4 times 7. So once I split this up, this becomes negative 1, square root of 4, and square root of 7. And if we do a little bit of simplifying, the square root of 4 is going to give me 2. The square root of negative 1 is going to give me I. And then the square root of 7, not a perfect square, so that stays underneath. Now, as far as writing, remember, multiplication is commutative, so technically I times 2 times square root of 7 is correct. But just to make things look nice, we usually put the number first, followed by the I, followed by any radical at the very end. So it's going to be written like this, 2i squared 7. This is not wrong, but it's not the preferred way to write it. Alright, so let's try another one. Square root of negative 12 times square root of negative 2. It's very, very tempting to go, oh, this is square root of 24. Just simply multiply the two things together. But no, that's not how it works. You actually have to simplify each radical first before you do the multiplication. So square root of negative 12, we're going to go square root of negative 1 times square root of 4 times square root of 3. Which means this is 2i square root of 3 times Over here, that's going to be square root of negative 1 times square root of 2, which means this is I times root 2. Now, when I multiply these together, the things that are on the outside are going to get multiplied together, and the things that are on the inside are going to get multiplied together. So we go 2i times I, which is going to give you a 2i squared. And then the stuff on the inside, we're going to end up with square root of 3 times 2, or square root of 6. Now, the big rule of the day is the one that we mentioned earlier. I is not only the square root of negative 1, but it also leads us to the fact that I squared actually is negative 1, which means whenever an I squared comes up, that whole thing can actually become a negative 1. So I end up with 2 times negative 1 times root 6, which gives me a final answer of negative 2 square root of 6. Alright, now, when we're solving, and a lot of times we will be working through trying to solve these, you got to keep in mind that x squared equals n results in 2 answers when solving for x. In order to solve for x here, I'm going to have to take the square root of both sides, which means x actually is the square root of n. But it's not only the positive square root, it's also the negative square root. So real basic, for instance, if I have x squared equals 16, a lot of people think, well, if I take the square root of both sides, x has to equal 4. Which is half correct, because it's not only positive 4, it could also be negative 4. Because 4 times 4 gives you 16, and negative 4 times negative 4 gives you 16. So don't forget when you're solving, we need that plus or minus there. Alright, so let's give one a try here. 5y squared plus 20 equals 0. Let's solve this for y. So first step, I'm simply going to subtract the 20 to the other side. So we'll get 5y squared equals negative 20. We'll then divide by 5, so y squared will be negative 4. Square root both sides, so y is the square root of negative 4, and here's where that last rule is so important. Whenever I square root anything myself, I have to have plus or minus, because it could be both answers. Square root of negative 4. Square root of 4 is 2. Square root of negative 1 is I. So in this case, we have 2 solutions, plus 2i and negative 2i. Now, what's the purpose of all this? Well, this is starting to introduce a larger frame of numbers called complex numbers. Well, where are these complex numbers? Well, what we know here is this box right here. And these are the real numbers that we've been working with. The real numbers are all of your fractions, all of your integers, all of your irrational numbers. So pi, e, 1/2, 2, negative 6. Those are all the reals. Well, if I take reals plus an imaginary number, then I get this larger plane, which is called the complex plane. And those are the types of numbers that we're going to be working with here today. A complex number is any number that can be written in the form a plus bi, where a and b are both real numbers. So a and b, these two come from this category right here, the real numbers. I is the imaginary unit. The a is what we call the real part. There's no imaginary number with this a, so that comes strictly from the real numbers. The b is what we call the imaginary part, because it comes from this purely imaginary numbers that we have here. And if we put those two things together with either a plus or a minus sign, that's how we get a complex number. So these are both examples of complex numbers, 5 plus 2i, 1 minus 3i. When you write a complex number, we're always going to put the real part first, we're going to put the imaginary part second. Alright, so here we go. Let's do some basic arithmetic with complex numbers. Good news here, this works exactly like you would think it would work. Meaning, if they're asking me to add two complex numbers, 12 minus 3i plus negative 9 plus I, I'm simply going to take my real parts, and I'm going to color code things here. So we're going to call the real parts red, so 12 and negative 9. And I simply add them together. So I go 12 plus negative 9 to get 3. I'm then going to take my imaginary parts, which we're going to call an I, which is a negative 3i, positive 1i, and I'm going to add them together. So negative 3i plus 1i leaves me with a negative 2i, and 12 minus 3i plus negative 9 plus i results in the complex number 3 minus 2i. Notice the red, that's what we call the real part, and the green is our imaginary part. Much like adding, we can also subtract. Same format, same method. So here we go. 10 minus 4, we'll subtract our real parts to get 6. And 2i minus 1i leaves me with a positive 1i, which means subtraction of these two complex numbers leaves me with 6 plus I. 6 being the real part, I being the imaginary part. Multiplication, once again, works exactly the same way. 7 plus 3i times 4 minus 2i. When I'm going to multiply these, I'm going to use exactly what you're hopefully thinking, and we're going to FOIL. So first, 7 times 4 gives me 28. Outside, 7 times negative 2i is going to be a minus 14i. Inside, 3i plus 4 will be 12i. And last, 3 times negative 2 is going to be a negative 6i squared. As always, combine your like terms. So we'll have 28 minus 14i plus 12i is going to give me a minus 2i, and then minus 6i squared. Now, here once again, our big rule's coming up. Remember the fact that I squared is actually negative 1. And if I can remember that fact, this becomes 28 minus 2i, 6 times negative 1, which makes this plus 6, which means my final answer, 28 plus 6, is going to give me 34 minus 2i. Now, we did multiplication, we did addition, we did subtraction. Last thing left on our table is going to be division. Division is the one that's a little bit tricky. However, if you remember how radicals work, it's the same idea. When we worked with radicals back ways, we did a technique which was called rationalizing. And if you remember those rationalizing techniques with radicals, it's the same idea with imaginary numbers. So the problem here, 5 plus 2i divided by 2, or 5 plus I divided by 2i, is I don't like to have I in the bottom, much like I don't like to have a square root in the bottom. So because I don't like the I there, I'm going to do what I do with square roots and say, okay, the way to get rid of this is I'm going to multiply the top and the bottom by I. And think about what you did when you had square roots. If you had a square root in the bottom, you said, I don't like that there. So the way I get rid of it is I multiply the bottom and I multiply the top by that square root. So 3 square roots of 2 on the top, square root of 2 times square root of 2, which is square root of 4, or 2 on the bottom, and this was rationalized. Same idea here. I don't like the I on the bottom, so I take that I and I multiply it by the top and the bottom. And when I do that, we get 5i plus I squared. And again, the reason why I get this is because we have to distribute. The I squared, remember, is going to become a negative 1, so I got a 5i plus I squared. And I have a 2i times I, which is going to give me 2i squared. Now, if I clean that up a little bit, keep in mind what this actually is. I squared is negative 1, and the real part always comes first. So I'm going to write this as negative 1 plus 5i over I squared, again, negative 1, so over negative 2. Other thing we don't want to do here is we don't want to leave a negative in the bottom. So I'm going to take this negative, this one that's right here, and I'm actually going to bring it to the top and I'm going to distribute it. So this is going to become 1 minus 5i over 2. One last thing that we do here with complex numbers, we usually don't leave them as fractions because we want to see this as two parts. We want to see it as a real part and as an imaginary part. So if we split this one up, we'll have 1 over 2 minus 5 over 2i. And what that allows me to do is it allows me to see my real part, and it allows me to see my imaginary part. One last thing we want to talk about when it comes to division is something called complex conjugates. And again, you've worked with conjugates before when you did some rationalizing. A conjugate is simply the same exact form that you have with a different sign in the middle. So instead of a plus, we have a minus. If it were a minus originally, we'd have a plus. Now, what the conjugate is for problems like this. 5i divided by 3 plus 2i. I don't like the division in the bottom. So what I need to do is I need to multiply by what I have. But I can't just simply multiply by I. It doesn't work that way. That plus sign messes things up. So again, you've seen this already when you dealt with square roots. If you had 3 over 2 plus 2 squared roots of 3, you would rationalize this by multiplying by the conjugate, which is 2 minus the square root of 3. So here, I'm going to multiply by my conjugate, which is 3 minus 2i. Now, when I multiply by this conjugate, I'm going to go through, I'm going to start and distribute my top. So we'll have 15i minus 10i squared. On the bottom, we're going to have to FOIL. So we'll go first, which is 9, outside, minus 6i, inside, plus 6i. Last, minus 4i squared. Combine my like terms, simplify the I squared, so this becomes 15i plus 10. And again, we're going to write the real part first. So we'll go 10 plus 15i. And here's the beauty of the complex conjugate. When you combine your like terms, the outside and the inside term should be opposites of each other. They should cancel completely out, which means I'm simply left with 9 plus 4. And again, remember it's plus 4 because of the I squared. So 9 plus 4 is going to give me, let's try that again. 9 plus 4 is going to give me 13. And then I take my answer and we split it up. 10 over 13 plus 15 over 13i. Real part, imaginary part. And that's complex numbers. Sorry about the long lesson tonight. There was a lot to cover. Hopefully it all made sense. Give the practice quiz on Moodle a try, and I'll answer some questions and do some problems in class tomorrow. Have a good night.